analysis, whatever you want to do that, this is a common framework. So here you can say that the text corpus is there, the corpus whatever you are collecting the data is there, and you are pre-processing the stop word removal NLP pre-processing is given here. And then the important part is the representation. The representation is here, and here this is the deep learning part. And this is about the knowledge discovery, what the classification you are doing, the deep learning as well as the machine learning, deep learning or machine learning. These two things I can say that the first two things are data and then pre-processing. I can say that this is the NLP part. So here the in between, the connection between the NLP and the deep learning is this representation learning. It's called representation learning. This is what we are going to see now in this lecture actually. So before that, I like to say something about the deep learning, then I will start directly to the representation learning. So this common framework for all most of the 80 to 90% of the applications in the text analytics. When it falls under the classification or clustering or regression, you can go for this framework. Not only that simple classification, even you can go for a structured output prediction. The output may be in a structured format, so that also you can go for this framework. So when you're talking about that last stage, the knowledge discovery, so it says about the technology, the technical things. So now I want to say about something about that machine learning and then the deep learning. I hope people are, I mean, lot of experts in this workshop also talking about the deep learning and the machine learning. I'm not going much detail about that. Just to say what is machine learning and then what is deep learning. So machine learning, I can explain machine learning in terms of a simple line equation y equal to mx plus c. So this is the way I used to explain machine learning. This is a simple line equation is enough to explain what is machine learning, particularly what is supervised machine learning. Where we used to say x is the data point and y are the labels. So x and y are the data and labels. So when you say the supervised classification, we used to have x and y. Say for example, what is that x and y? So we discussed about the age identification. So say the x may be the text content and the y may be the age group. So whether he belongs to the age group, say for 10s, 20s. So I'm saying the age group 20s. This text belongs to 20s. This text belongs to 10. This text belongs to 20s, like that. So the text content we can call it as a x, and then that label 10 or 20 or that is we used to call it as the labels or y. So this is called supervised classification. You have x and y. In unsupervised classification, you don't have a y actually in your hand. You used to have only x. So earlier the question asked about the fake profile identification. So that if they want to solve in the supervised way, so as I said that the problem can be taken as a model wise and then they can solve in the small models, age or gender occupation. In terms of, there is another way to solve that, say in an unsupervised way. So where you can collect the profiles, you can collect you collect some 10,000 profile information you collect. From that, you just cluster it and which may be the fake profile and which may not be the fake profile. So that is without any information of whether this is a fake or not fake. You need to cluster it and then say that which is a fake and which is not fake. That is unsupervised model. So when I say about the machine learning, supervised machine learning, I talked about x and y. So x is the y equal to mx plus c. Also I said that. So I explained what is x. X is your data point and then y is your output classes. So what you want to find from this equation? So x and y, you know x and y. The x and y are known variable. Now what you want to say is you want to find out the unknown variable here is m and c. These two are unknown variables. You need to find out m and c. That is the motive of machine learning training. There is two components in machine learning. I hope you are aware: the training and then testing. When you say training, your objective is to plot to fit the data in this equation to find what is m and what is c. What is a slope? I mean, if it is a line, if it is a line, if it is a sometime it will be a plane or sometimes it will be a hyperplane, or it's a multi-dimensional plane. So here I'm just talking about the two things, M and C. So we used to call this M is a weight, W-E-A-G-S-T. So I'm just representing as a weight, W, and C we used to call it as a bias. So as I said that the output of machine learning training is weights and bias. Set of numbers is the output. Machine learning or deep learning is just a numerical, the mathematical algorithms. So it won't work with any images or text or signals, whatever you are passing. The thing is you have to convert that into some set of numbers and you have to pass to the algorithm because it's a mathematical algorithm. So this is the W and B is a training. This is also again a numbers. W is a matrix and B is a you can consider as a vector. So when the testing comes, you have Y and B. Testing means what? I have something, a new X cap I have, new data points I'm having. I don't know what is Y for that. You are going to check that you are passing some profile and then you are going to find out whether that is a gender is what is the gender of that particular profile. So in that case, what I can do that, what you know here, you know W and B. Okay, you know W and you know B. Fine. So and you have X cap is given. So you have X cap also in your hand, you know X cap also. So the X cap is the new data point, whatever I'm giving. X cap you are taking. So you are applying here W X plus B. So that as per the equation that is called Y. So that is called, here we are calling it as a Y cap. The Y cap is the label whatever you want. So this is the way, this is called a testing. This is the way to find out the labels in the machine learning. This is the simplest way to explain the machine learning with respect to the line equation. Fine. So this is the machine learning. You have seen that. So supervised learning is what I explained. Supervised learning, unsupervised learning means only with the X. Hybrid models are there where supervised and unsupervised plus the knowledge-based model. The knowledge-based model means it's called as a rule-based system, where you will write a set of rules. Based on the rules, the system will take a decision. You are writing the rules to make a system to take a decision whether this sentence belongs to particular X class or whether it belongs to Y class. So this is the hybrid. This is a hybrid model, hybrid modeling. So what makes this from the difference from that deep learning model? When you talk about deep learning, I have slides here. So when you talk about that deep learning, it's also called as a representation learning. So I'll explain a little bit about what is that machine learning in terms of architecture perspective. Then we will say that how it's different from deep learning. So this we'll say later. So the deep learning, this is the definition of the deep learning. So it says about the several levels of nodes. But the real meaning of the term deep, why the term we are calling, why the way we are calling it as a deep. So this is how our brain works and then our brain understands the things. So how you understand that? Suppose you are, I'm talking about the Dr. Qasim Murugan sir is that. So if you have seen him, so how you will recognize that he is Murugan sir? Tomorrow you know that you have seen his photo and fine. The 5 days workshop you spend the time with him, fine. You have seen his video also. Next week or next month you are visiting somewhere and then you are seeing that, you are seeing his face from the long side. You can easily recognize that. Yeah, this is a Murugan sir. How your brain recognizes that? How your brain knows that he is Dr. Murugan? How your brain recognizes? So this 5 days, it's trained. The brain is trained. The different pictures of different images of his face images is recorded in your brain. So it's stored somewhere. And whenever you are seeing that, whenever the new image it comes, it's matched with that. So it fires a particular neuron. So it's take the annotation. The annotation is here. It's a Dr. Murugan. Then it says that it's a Murugan. This is the way how our brain works, and then how our brain recognizes the objects. How the information is stored in the brain. That is very important, because like we used to say that brain is a huge. It's a kind of a huge hard disk. But interestingly, the information is stored in a conceptual manner, in a hierarchical manner. How it's stored in a hierarchical manner? Suppose today you are seeing a car. You used to see a car with the 4 wheels. Today, you are seeing some car in a road. You are seeing the car with say, some example, 7 wheels. So suddenly that information will be stored in your mind. Where this information, where this image about that car, the information will be stored. It will be stored near to that car because your brain already knows that car. 4-wheel, and then whenever I see that car, if you just close your eyes, means you can imagine that the car color, the favorite color of yours, or whatever the color you have seen more, it will come, and this is the thing. So when you are seeing that car, new car, it will be stored near to that car, and that the generally where the car information will be stored in your brain. Car information, if you closely see that car information will be stored in the vehicle, in the vehicle, I can say that the vehicle is a class, and then car is a one type, like that will store hierarchical. And if what type of car you are saying, the brand of the car, so whatever car you are saying, the brand will be stored here, and maybe the other features like the name of the car. So brand of the car, the name of the car, it will be stored like that. So our brain stores the information like this. Before saying that, if you are saying the car, if you are seeing a car Skoda, if you are seeing in a different color, if you are seeing some kind of ash color, the information again will be stored. Vehicle, you are seeing car, you are seeing the brand, whatever the brand you are seeing, the color or the name of the car, it will be stored like that. New brand or new name of the car, new car is releasing, so that will be stored like this. So the in brain it's stored in a hierarchical way. So same way the deep learning also going to work. So that's the reason we are calling this. This is the reason this says that the deep. This is the reason we are calling this as a deep learning. So deep learning also try to extract or try to store or try to understand the information how a brain is doing. So it's not like directly if you are giving a car to the deep learning model, it's not blindly going to say that this is a car from this so and so company. First, you try to understand that is it a vehicle. Next level, next layer, it will understand that this is a car. Next layer, it will understand that this is this brand, particular brand. Next layer, it will understand that whether it's a SUV or other type. Then finally, it will come up with the name of the car. So whatever I said is the layers. So this is how the deep learning is. The deep learning is nothing but it's mimicking the function of our brain. So that's the reason why the deep learning is popular. Machine learning is not that way. Machine learning, they haven't tried to mimic the way how our brain works. That's the reason we used to call deep learning we used to call the deep neural networks also. Okay, so I don't want to say much about the deep learning trends because it's a buzzword now. As you know that 2016 itself it reached the peak. It reached the 100. It's one of the important one of the Google trend board still now. So the reason actually it's not only the deep learning entered in the area of NLP or the computer vision. Initially it started with the computer vision and speech processing, image processing, and biomedical domain. So like that, it's moved across everywhere. Now, wherever you are having the data, then there will be a deep learning algorithm. So there will be deep learning. There is a possibility to work with a deep learning. So now the deep learning is not a common field. Deep learning is now it's a common field. So just some slides about how the deep learning comes to the picture. So when you say that 1950s, 46 is the first computer, first ENIAC, the first computer in 46. Interestingly, the famous mathematician Alan Turing in 47, in a 1 year, 46 to 47, in a 1 year, he is proposing the concept of, is terming the word artificial intelligence. See that AI, even though we are calling it as a buzzword now, this is we used to call it as a AI boom. AI term coined in 1950s itself. There are a lot of 2-3 booms are happened. Now whatever we are having is we used to call it as a third boom of AI or a fourth boom of AI. The first boom when the AI comes into picture, people started with the reasoning algorithms and people say that AI will solve any kind of problem. After 10 years of research, they understand that. So with the present data and then with the present computational power, whatever they are having, they cannot solve every problem with the help of AI. Later, SVM, once SVM comes into picture, sorry, before SVM, the neural networks, in between neural network is there, yeah. 879. Neural network substitution picture again, that is called the second boom of AI. So second boom in the 80s. So after in 2000, when neural networks popular, then we can call it as a, we are not calling not neural networks, SVM. We are not calling the SVM is a part of neural network model. We used to call it as a different type of machine learning model, called methods. But that was popular. After once people understand the problems in neural networks, people started moving to after 90s. After 1991 only it started. People started moving to SVM. Still, SVM is powerful. You can see that some still people are publishing paper with support commissions. And once after, if you see that when the deep learning becomes popular, 2006, the famous person Hinton, the Turing Award winner, Hinton publishing a paper about the deep learning model. So in 2006, that time it's gradually started its trend. 2010, then people coined that this is the third boom of AI. From 2010 onwards, now if you see that there is a you can see the function is that is not going down. It's going in the other direction only. It's a rising direction only. So that's now whatever we are having, we used to call it as it's a fourth boom of AI. Okay, this you know that AI is a superset, and machine learning is a subset of AI, and deep learning is a subset of machine learning. So what's the difference? This is the year wise when AI started, when machine learning started, when deep learning started. Sorry. So what is that? What is the application behind that AI? If you closely see that, so not as I said, that not only pertain to image processing or computer vision or language processing. All other areas wherever data is there, you can apply the deep learning or artificial intelligence. You can say that cognitive cybersecurity, neuromorphic computing, it's a new areas. So deep learning and the applications are given here. Machine learning, deep learning, and autonomous systems, autonomous vehicles. Most of the softwares in India are working on the autonomous cars. They are working on the small model of the autonomous cars. So cloud robotics, and then you can see here the chat box. NLP is here. NLP and chat box are here. So this is that. So now I'll just take this time to say that the difference between the machine learning and deep learning models. So when you say that deep learning, yeah, I think my voice is audible now. Hello.
Yes, audible, Anand.
Yeah, fine, thank you. So, when you say the difference between the machine learning and deep learning, what machine learning is doing is it's taking the input data and with the help of human, it extract the features. So human influenced feature extraction, and it's going for the classification. This is the usual machine learning model doing. What deep learning is saying is, I don't want that human. So why you are giving that process job to the human? Usually the human will be a domain expert. If it is an image processing, then it will be the computer vision expert. NLP means NLP expert. Usually it will be a data science expert or a biomedical expert who knows about that domain knowledge, who knows that domain, because they only can give the features. If you are asking me to give a features to the biomedical data, I cannot give. A biomedical expert only can give. If you are asking me to give a data about the NLP, I can say that. You can consider the lemma as a feature. You can consider whether the stop word is included or not, word embedding is there or not. So I can say that's a feature. So, or the positive word is a feature, negative word is a feature, like that. So that is given by the human feature extraction. That is the usual machine learning model. What deep learning is saying is, why you want that expert? You replace the expert with the deep learning expert. That process also is due to the algorithm. Algorithm will take care of that feature extraction process. That's what we are calling this as a feature learning model. Feature learning model. It's learned the features by its own way. So the other difference what we want is machine learning. If you have a small number of small data set, you can go with the machine learning model. But if you have a large data set and good computational power, you can select the deep learning models. So these are the comparison with respect to the machine learning and deep learning. So small data set on large data set, it's quick to train the model. Machine learning, deep learning is computationally, it's an intensive task. Okay, what is the trend? This is a trend, it's saying with respect to the amount of data. So you can see here how the performance varies with respect to amount of data. X-axis says about the data. So red color says about the learning algorithm, say talking about the machine learning algorithm. So what will happen after some time? The red color, if you see that after some time, after you increasing your data, so you have a 5,000 data here, 10,000, 20,000, 30,000, 40,000 data you are here, 50,000, 60,000, like the data size is increasing. But after a certain point of time, the algorithm, it won't show much difference in the performance. See the performance here, it's reached to 70% suppose. But even though if you're increasing the accuracy, it's very difficult to algorithm to reach the 80%. That's a way in the most of the learning algorithm, apart from the deep learning model. But in the deep learning model, the beauty is, even though after some time, if you are increasing the data, if you are increasing the data like this, if you are increasing the data, see that what happening, the algorithm is, the performance of the algorithm is keep on growing. So that is the reason why the deep learning is so popular. And then it says the performance of the deep learning is highly depend on the data set size. So this I already said that the traditional deep learning and then traditional machine learning and then deep learning, and these are the Google searches. So it's already reached 100 in 2017. Yeah. He is a very famous person, Andrew Ng. So if you know about the Stanford lectures, so his lectures are very popular, machine learning lectures. So his statement, I have worked all my life in machine learning algorithm and I have never seen one algorithm knock over benchmarks like deep learning. So that is his statement. So he's a machine learning person. He says about some algorithm which knocks all the benchmark. Not in one domain, all domains. That is an interesting fact. Okay, now we are coming into respect to the NLP, how that NLP takes a deep learning model. In traditionally, if you see the traditional models or classical NLP is like this. So you are having the documents, you are detecting the language, and you are going for the pre-processing. You see that each language you are having a separate pre-processing. You are having the modeling. Each language you are having separate modeling. Not only each language, the modeling sometimes will be different based on the task. Sentiment, you have to do the different modeling. Sentiment, you have to say that you have to find the positive words and negative words. But in order to find the age group of the person, you don't want the positive words or negative words. Entity extraction. So you have to analyze whether the letter starts with capital letter or not. So here in a sentiment, we don't want that information. So each application, each task, whatever we have discussed, so its own modeling, and then it won't structure in that classical model. But that is replaced in the deep learning model. The deep learning based NLP, if you see that this is the current architecture of deep learning based model. So documents are there. So what is happening? You see that the documents are given to some model called embedding. Sorry. So what I'm going to see here is actually this embedding only, the dense embedding. So documents you are giving, this is a documents, and this completely it's a deep learning model. The applications, whatever we discussed this morning, that's applications, it's a deep learning model. So now what I'm going to, after this, what I'm going to talk is, I'm going to talk that how can you convert the document to the dense embedding? Because this is one of the important one in the NLP and then deep learning model. As I said earlier, machine learning or the deep learning models are mathematical model. It knows only numbers. You cannot pass the text or you cannot pass the image to them directly. So what you need to do is you have to pass the numbers. Numbers should be meaningful numbers. How to make a meaningful numbers? So the interesting fact in the image processing is pixels are meaningful numbers. So white color dots will be in a different pixel value, black color dot will be different, red color dots will be different. So that way you can understand that okay, this says about a particular object. This object is different from this object, but that is not possible in a language. Because what we want is, that's the reason we are going for the dense embedding. So I'll explain that how the dense embedding can be useful. What is dense embedding? How it will be helpful for finding the numbers, and then how can you know that the numbers are efficient? Because it should not just simply with the random numbers. The numbers should be efficient. We'll see that how can we say the numbers are efficient. So these are the applications. Morning itself we have seen the application. These are the other applications pertaining to the NLP. When you talk about the deep learning, so this is an interesting image. So where all the deep learning architectures will be given. Just to see that whatever, if you are really working the deep learning, whatever deep learning architectures are there, whatever deep learning architecture you know that you are working, just to see that it's a clear explanation of how it's working and the this is from Van Beam. So this will be interesting one. So how that will inquires in other things. This we have seen that. Okay, yeah. This we have seen that. These are the other applications only. Also, morning explained that how system is understanding the language. So say there is a command in the there is a tweet literally says that literally your Facebook message app is useless. You only want it to increase profit. Please fix yourself. It's sad at Facebook. So people talking about Facebook. Organization is the Facebook. I'm talking about a particular product of the Facebook. That is a message app. So what the sentiment I'm giving useless. So I'm saying I'm using adjectives. I'm saying my tone here is a negative tone. I'm talking negative about some product. So emotion is I'm frustrated because I'm using the word sad and useless. And language is the informal. You will see that I have used the word you are. Literally, your Facebook, you are have used instead of you are. Yeah, this is some of the other applications related to the big data and in healthcare. We already discussed about the applications. So I'll just directly go to the dense embedding model. Okay, so now I just entering into the dense embedding model. It's called as the word embedding. So this word embedding is invented in 2014 by the famous person Nicolo. Now he is in Google. Now if you see that in the last 6 years, this word embedding ruled the NLP field till 2018. Till 2018, word embedding was very popular. But now, there are other embedding models are there. The models like BERT, B-E-R-T. So this is like an extension of word to work only, B-E-R-T. So they just identify the flaws in a word embedding, they recovered in the BERT, and then they introduce the BERT model. Now this is a popular model. Yeah. So as I said earlier, the word embedding. So why we are going for word embedding? And the word embedding is also called as a word to wake. So you can see here word to wake. It means that word is going to convert to a vector. Sorry for me. Yeah. Word, the document I'm giving input a document to the neural network model, I'm getting some output. This is the input document I'm giving some. My output, you see that each word in the document I'm taking, I'm representing with the set of numbers. What I want is the number should be meaningful. This is called word embedding. So why we want the numbers? So as I said earlier, the one part is deep learning models knows only the mathematical numbers, because machine learning or deep learning is it's nothing but it's a set of solving equations. So we are solving a set of equations. So when you are solving the set of equations, then you cannot pass the text content. So you should pass the meaningful numbers. So for that only we are going for the dense embedding, and we want the effective representation. It should not be like just a representation, like a random number or ID. So wherever the word starts with A, I can give one, like that. The number should be meaningful. How to make that meaningful? So if you are representing words as a meaningful representation, then the sentences will be meaningful and the text complete the document will be meaningful. Okay, so earlier, before word-to-word model, there are popular models called the one-out representation. This is the earlier model. 80s till 90s, people used to have that one-out representation. But now also we are using one-out representation. One-out representation we are using as a part of dense embedding model. But earlier, one-out representation, only people used to have only one-out representation. What that one-hot representation? The term says about one hot. In a particular time, only one place is active. That is a one-hot representation. It means that in a vector, one place is active. All the remaining places are zero. It means that this place says about the particular word. Suppose I'm having the word water. I'm having the word water. So in the place of the water, it is 1. All the remaining places, the values of the vector is 0. So this is called a one-hot representation. So 1 for the target word and 0 for other words. So this vector size, the vector size I can say that R of V. What is V? V is a vocabulary. So vocabulary means, what is vocabulary? Can anyone say what is vocabulary? I hope you people are listening. Fine. Okay, so I'll come up with other question. So the vocabulary says about the unique words in the corpus. Unique words in the corpus. Suppose that suppose this you have taken as a corpus. That this particular slide you are taking corpus. For occurred 2 times. So I will consider only once. For yeah, vector also occurred. Vector occurred meant 2 times vector occurred. So 1 time will take. So the unique words are used for the vocabulary. So if you are counting the vocabulary of this particular slide, so 1 is the first one, vocabulary size I'm saying that. So 1 is a 1, 2 is a hot, 3 is a representation, 4 is a, 5 is a vector, 6 is off, 7 is a length. Idea, I'm just calculating unique words. 8 if I'm calculating B as a unique word. Again 1. Sorry, 10, 11 is the, so like that it will go on. But here the interesting thing, you can see that the number 1 and the number 9 are having some similarities, number 1 and 9, because this says about ONE and this says about 1. They are somewhat similar words. But here in the one-hot representation, system don't have any mechanism to find the similar words, because each word is represented in a different dimension. Each word is represented in the 90 degree. So the vocabulary says, if you are saying that you have a 40 means R of 40. R of 40 means each word in the corpus can be represented with the help of the vector size 40. Out of vector size 40, one place which word you are mentioning, that one place will be 1, all the remaining places will be 0. So as I said that the problem is one-hot representation. So I'm taking the 2 vectors of the 2 words I'm taking, hotel and then motel. So see the vector of hotel, see the vector of motel. So I'm just taking, I want to find these, I know that these 2 words are similar. I want to find out whether these 2 words are having any relationship or not. I'm just taking the dot product. It means that I try to find the distance between these 2 things. Or I want to find the similarity between these 2 words. If I'm getting the value, dot product value higher, then the 2 words are semantically or syntactically similar. If I'm getting less value, say 0 or say 0.0001, then these 2 words are no way related. So, but if we pass the motel and hotel in that one-hot representation, I'll get the value 0. It means that system is saying that these 2 words are nowhere related. So how can you make these 2 words are related? Because if you are saying that these 2 words are related, then the classification or the other algorithm can handle the things easily. As I said, the conceptual knowledge, already the system knows about the vehicle. Now you are telling that, instead of telling the car, if you are telling that vehicle is a part of car, then the system will understand, okay. Then you are telling that the car brand is this one. After that you are saying that one of the car name from this brand is this one, then the system will easily understand that what you are talking. Instead of simply pushing something like a wagon, or you are just giving to the system and then asking system to understand what is a wagon. So you are mapping with the conceptual concepts, hierarchical concepts. So that is that way how we are going to see that. We'll see that. And we have seen the problems in the one-hot representation. The other model is LSA, latent semantic analysis. So this is based on single value decomposition. So people try to solve the problem in one-hot representation. One-hot representation. The other problem is dimension, because as I said about unique words. Yeah, unique words I said here. The unique words R of V, as I said, the unique words. Sometimes in the unique word size may be huge. So if you take the Google corpus, the unique words are 13 million. So your vector size is 30 million. In a speech corpus, the vector size is 20,000. In PTB, Pentry Bank corpus, the vector size is 50,000. 50,000 words. Each word, it means that each word you are representing with the help of 50,000 numbers. Why you want that huge number? Instead of that, why don't you want that huge? Even though it's a huge number, it's completely sparse representation. So you should go for that dense representation, and you don't want that bigger number, so you should go for the low dimensional dense representation. That is the motive of that word embedding. So here the SVD, it solved the problem in a certain level. It solved with the dimension. There is the option to reduce the dimension, but the problem here is the computational cost. The computational cost is too heavy. You can see here order of m after order of m n square. So that's a reason that why this model is not used widely. Okay, now we are going to come to what is the recent model, word embedding model. So before that, so I want to say the statement by the famous linguist Firth. So he said the statement, he coined this statement in 1957. He coined the statement like, you shall know a word by the company it keeps. Listen, again I'm repeating, you shall know a word by a company it keeps. What does it mean? Can anyone respond? You shall know a word by the company it keeps. So it says that you can understand the word by knowing its nearby words. Even though if you are not knowing the particular word, it's no problem. With the help of nearby words, you can understand this particular word. We'll see that. I have an example. I'll show that. So this is called a word-to-word embedding. How this word-to-word embedding is working? The main mantra of the word-to-word is don't go for prediction. Sorry, don't go for count. Go for prediction. So usually the earlier model, it goes for the count. How many times the word occurred. So the current model is the recent model word-to-word is going for the prediction. Instead of saying the statistics, instead of taking the statistics, it's going to predict something. So it's represent each word in a, as I said, that low dimensional dense vector. So here the other advantage is the vector similarity, whatever you are calling it as a that you can see here, that is word similarity. So that's the reason why we are converting that words to in a vector form. It means a set of numbers. So the key idea why we are doing that, predict the surrounding words of every word. Again repeating, predict the surrounding words of every word. This is a key idea. We'll see that how it's doing that. So as I said that the mantra of the is don't go for counting, go for prediction. You are making a machine to predict something. Before giving to the actual classification, you are predicting. Usually in classification only the prediction part will start. But here in feature extraction itself, the classification the classification model what it means it's trying to predict something. So at that stage, once it's a train, then it can be reused. This is the important one. Once it's a train, it can be reused. It means that if you train the model once, the model you train, then if you are taking purpose, if you keep it, it can be reused. Reused It can be used in any other application, not only the sentiment analysis, not only the age reduction, gender reduction. So whatever, because this is the initial point. This is like everything you are doing. Whatever text is there, you are converting it to set of meaningful numbers. So obviously this
Dr.
is
Anand, excuse me, Dr. Anand, your voice is breaking.
oh,
Not clear.
not audible. Okay,
Yeah,
one
not
second, sir.
audible.
Thank you, sir. I just off my
Yeah,
microphone. One
yeah.
second.
Okay.
I just changed my situation. That may be the reason. Is it fine now, sir? Hello, sir. Is it fine now?
Again the same, little break.
One second. Is it fine now, sir?
Yes, it's fine.
Oh, okay, fine. Thank you, sir. So the word-to-vec, so once it's trained, it be used. It means that once you train the model, it's not like the word-to-vec it's used for only sentiment analysis or only for particular application. It can be used for any application. That's the reason I'm saying that it's once it's trained, it can be reused. So it's for the fresh perspective of all problems. Whatever I discussed in the morning, we can use the word-to-vec because it's the first level. So after doing the stopword removal, after doing the pre-processing, you are converting the text into some meaningful numerical values. So that is the word-to-vec. So interestingly, this one solves the many problems. The one solves the many problems of language processing. So these are the other two advanced things, subsummary hierarchical softmax. This I think we don't want now. It's out of scope of this presentation. Okay, now I'm just going to talk about how the word-to-vec model is working. What is the methodology? What is the algorithm behind it? Before that, I'm just asking a quick question to you. So here, I blurred some word here. You can see here, some word is not visible here. I blurred that. So why don't you find out the word and then in the chat box? $30. I hope you understand my question. So I blurred some word purposefully to try to find the word and put it in the chat box. So copies of corpus, yeah. It says about the unique words. So some questions people ask, large data set means how large should be the data set size numerically in deep learning. So it's based on the application. So preferably 1 lakh sentences if you can go for the deep learning will give better results. The words which you remember, you can use collection of words. Vocabulary you are saying, I think, lexicons. Yeah, lexicon is the other answer for vocabulary. So I asked about probably Akila probably love and Nasruddin Ahmad also love. Parimala Kanadevan love or like Jitendra Pandey love. So the answer is love. So how you understand that? Whether you have seen the slide earlier, how you understand that? So you have seen the context. So this is what I was here. So you back to the statement. You shall know a word by the company keeps. Even I hide a word, you can understand. I have given only the company. Whatever I have given here is a company. Am I correct? But you found the target word correctly. So that is a thing that is a power of word. But the same concept is this one. The same concept, the same mechanism we are going to replicate in the word-to-vec embedding. So before going to the algorithm, what we want to achieve finally in the word-to-vec model, what do we want to achieve? So as I said that the word-to-vec model is a low-dimensional representation. Low-dimensional means that it will be a dimension of 100 instead of 50,000. It may be the 100 of 300. The most frequently used dimension in the worldwide is 100. Again, it's a hyperparameter. People fix 100 and 300. People are getting good 300. If you really want to change for 1,000 or 1,500, it's welcome, but it's a waste of time. People have done the research, have done the enough analysis, and then they fix these numbers 100 and 300. After converting this 100 and 300, I want to be asking that You are asking that, so telling that go to work, this and all will be efficiently to understand the body. So how can you prove that, sir? You are asking. Because I have 100 numbers in the hand. If you are asking me to prove visually, I cannot. Because as you know that the picture speaks a lot rather than the words, rather than the text. So what I can do is, out of 300, I can write a small, with the help of PCA and TSME, I can convert that numbers into two-dimension number. Two-dimension numbers means only x comma y, 2, 3, 2, 3, 4, 5, 5.1, 4, minus 1, 3, like that. So this 100 dimension to only 2 dimension. So there will be heavy loss in that. Only we can capture only 50% of the information, only in the not even 50% information in the 2 dimension, because we used to have 100 dimension numbers. We are converting it to 2 dimension numbers. Why we are converting the 2 dimension numbers? To show you realization how the is powerful. After converting into 2 dimension, I'm just plotting in this XY axis. You can see here, I'm just plotting the word. Suppose this is the point says about the director. This point is a x value and y value car. So if we want to say that the vector of the owner, say roughly the 0.3 comma 0.3 is 1. Women, I can say that this is a 0.6 comma 0.4. 0.6 comma 0.4. So these numbers I reducing the representation is plotted here. Here, what can inference that we put it in a chart box? What's the inference of this figure? Next call. What is the inference of this figure? This gives a similarity. What kind of similarities exist?
Sir, voice breakdown, sir, little bit.
What kind of similarities exist? Is it fine? I stopped actually. I asked the question. What similarities exist in there? The inference from the diagram. Similar words are held together. Yeah, correct. So if you see here, colors blue, pink, relationship words. So remember, this is the only the result in the 2 dimension or 2, because only we can see only the 2 dimension. I mean, in the computer monitor, real time we can see up to 3 dimension, but we cannot see how it's working, how close it's the dimension. But even though it is a 2 dimensional, this is this much inference you are getting the 2 dimension. Definitely in the 100 dimension, it will be more accurate. So this is the inference, one inference of the clusters. Automatically you can identify the clusters. So remember, I have given only the text content to the machine. I haven't given any information about this is a color and this is a relationship. No, only the text sentences I'm giving to the machine. So machine can able to understand the clusters. What else is one more inference is there here? So one more inference I can say that see the 2 different other words, dad, mom, man, woman. Yeah, sister and brother, aunt and uncle, grandfather, grandmother. I'm just counting 2 things. Father, mother. Yeah. See the direction and then see that for all this relationship, all the words, masculine and feminine word. So that is falls under the similar regularity. This is called a regularity. The direction is somewhat similar. As you know that we are calling this as the vector. Vector means we used to see that magnitude and direction. Well, whatever we have seen is a magnitude. The father and son is closer. The daughter and then the grandmother, the terms are closer. We have seen in terms of magnitude. Am I correct? But the direction, but here you see that direction also have some information. This is the direction I'm saying that. This direction says that regularity says that these 2 entities are one represents a male, means other represents female. We haven't given any information to the system. We are giving only the data. getting only the sent data. Meaningful sentences in the system, 1 lakh meaningful sentences. But system is coming up with the references like this. That's the power of word embedding. Other example, if you see that king minus man, vector of king I am taking the numbers of king. From that I am removing man. From the king, we know that king says about the masculine gender. From that I am just removing that masculine information man. I am adding women. After adding that vector women, I'm getting that approximately I'm getting the vector which is close to that queen. This is a even you can test. So this is the one or another other power of the word embedding. So how that word embedding or producing meaningful representation. Okay, now we are coming to that. We are coming to that model. How that word embedding models are working. So I just to go back to this one, and then I would like to explain that word embedding model here. So when you say that the word embedding model, there are two types of word embedding models are there. One is called CBO model, other one is called skip-gram model. CBO model and other one is skip-gram model, or simply we'll call as a SG model, CBO model, CB model. So what the CBO model will do? So we are talking about two things here. One is a company, other one is a word. Am I correct? Go back. You shall know a word by the company is, it's a context or nearby word. So what I can say in the CBO model input is, so the input is context. Context, you are giving input to the machine. You are asking the algorithm to predict the word. So this is called CBO model. Input is context, output is words. So this is called CBO model. So other model is a skip-gram model. This is a reverse of CBO model, where the input is, what will be the input? The input is words and the output is context. Okay. Now I ask you to solve something. Earlier you solved that you found the word love from this slide. Now I'm asking what you have done, whether you have done the CBO model or skip-gram model. 30 seconds. So again, I'm repeating the question. So already you answered the question that what is the blurred word here. So what experiment we have done? Whether we have done the CBO model or skip-gram model. CBO model means input is context, output is word. Skip-gram, input is word, output is context. 30 seconds. Yeah, most of the answer says about CBO modeling. The CBO model is the correct answer. So why CBO model? You are giving the context. Context is the company. I have completely given a company to you, and I ask you to find out the single word. Again, repeating single word. Skip-gram, it's completely different. I'm giving only a single word to you. I'm giving a word only love to you. I'm asking you to fill all the remaining words in this slide, whatever I'm having. I'm just having this slide. I'm just giving only the word love. I'm asking to fill all the words related to all the word associated with this. That is called skip-gram model. Skip-gram and then word to CBO model. So this is the diagram says the word. You can see here. So this is a CBO model and this is a skip-gram model. So context is given here. Context says about W minus 1. Left minus 1, left 1, first left word, left 2. Left context, right context. Suppose I have a 5-word sentence. 1, 2, 3, 4, 5. I'm taking 5 words. Any 5 words. Here I'm taking use a window of word. Here, use is a WT minus 2. Here is WT minus 1. Sorry for that. Window is your target word. Off is your or 1. word is your R2. In your corpus, in your text content, you are taking a words of 5 size, 5 window size you are taking. Each you are, this you can see here, this is the output. Okay, the window is output. So this window you are not showing to the machine. You are hiding. How I hide the word love to you? Like that you are hiding this word. You are telling, you are just giving it as a fill in the blanks. You are giving the system like use a underline of word. sorry. You are asking an algorithm to predict what is the filling the blanks word. But the algorithm, the same algorithm knows that what is the middle word. The same algorithm knows that the word is a window. It is keeping it as such. It is a while. You are saying that use a say suppose use a door of word, and whether you have whatever word you are having is correct or not. You are given a word door and I am having the window. No, it's wrong. Now again you are saying use a computer of a word. Something is given. No, it's wrong. Instead of saying that just a wrong, you are saying that wrong or right. You are saying that how much error. The error can be calculated like, how can you calculate the error? Whatever you are having the word window minus the word door. I'm saying of these information, that is error. So you closely see here. So there is no complex architecture here. This is a simple one-layer neural network architecture. What you will do that, so once you are learning that, you will get the error. In the neural network architecture, what you will do, you will have an input, you will have output, you will have a weight vectors and bias. Once you are not satisfied with the output, once the error is there, with the help of error, what you will do, you will update the weights. Same thing I'm going to do here. So I'm finding this error. This is the error. Using this error, I'm going to update this weight vectors. The weight vectors is nothing but it's going to be the finally the word vectors. So in a terms of once again I'll explain the example. So this is a SIBO model. This is a skipgram model. Okay, I have another example. I'll explain once again. So before that, how it's doing that? What is the mathematics behind that? So if you closely see that, it's finding the log probability of the next word. So the bigram it's finding, the bigram probability. So again, I'm repeating. So people will get confused. So Sir said that this is a predict-based model. It's not a count-based model. Then why the statistics is coming here? But preferably in the prediction case, we won't use statistics. Only in the count-based model, we used to have a statistics. Am I correct? Prediction-based, count-based model means how many times the word occurred, how many times the diagram occurred. So divided by this one. Then it's a probability. Then it is a statistics model. But why here the probability is there? Remember, I'm not going to use the probability as a score. I'm going to use the probability as a function. So what I'm going to do, I'm going to maximize this probability value. I'm not going to calculate the probability, and I'm not going to take the decision based on the probability. So again, I'm repeating. So I'm going to maximize the probability. How can I maximize the probability? So that's the reason I'm just making it as a optimization problem. So it's a constrained optimization problem. So this m and m or the window minus m is the window size. Here we have a window size of 2. Minus 2 to plus 2. We have minus 2 to plus 2 words. It means that 2 words from left, 2 words from right. I'm not considering the middle word because I don't know middle words. That is my objective function. I'm not considering middle words. All the remaining words I am doing here. You see that, suppose the j value, if you're taking a 1, so wt plus 1, t plus 1, and wt. So the given wt. So you are find the t says about the window size of sorry, m is the window, t says about the capital T says about the vocabulary. All words in your corpus. So each word you are finding the probability. Each word, for each word you are passing here, because t you are passing here, wt, each word you are passing here. In your corpus, each word you are passing. Look at, again repeating, in your corpus each word is coming here, but here the window of 5 word, as I said that I'm taking the window of 5 word here, suppose 1, 2, 3, 4, 5. Here the t plus 1, this is a, suppose, okay, this is the middle word, suppose you are treating. Only these 5 words you are taking. In is that minus 2 word, this is a minus 1. A you are considering. This A given word, what is the probability to be that the next word is a A? So this is this WT is for whole words in the corpus. That's what T is the vocabulary. So that way we are finding, and then we are taking the average for all words. We are finding the probability, and then we are taking average. So this value I need to maximize. This is a score. So I want to maximize this probability score. If it is maximized, then that particular m value, the particular WT is the right. The parameters. You can say that if this probability, if you may make it maximize, whatever you achieved in the parameters, the j of theta is the parameters, hyperparameters. Whatever parameters are achieved, that is suitable for your model. This is what you want to optimize. So this is a SIBO model. So I have explained about the SIBO. We have seen the power of row-to-earth model. I explained the 2 different models, SIBO explained, and skipgram also. Skipgram is same here. Here we are giving only the word window. Say, take the same example. Use the window of a word. I'm giving only the word window. I'm hiding all the words. I'm hiding the word use, yeah, of word. I'm asking system to find out the word, whether it's a use or yeah or what is the words, what is the 4 words. System I'm asking to find out. That is called skipgram model. Again, I'm having one more example. So this is just whatever I'm explaining, the theory is given here. Anyway, I'll share the slides. You can just go here. The important thing is there is no activation function between any layers. That's what, as I said, that this is simple neural network model. It's not, it's a shallow network model. It's not a deep model. So whatever error we are calculating between the output and target is propagated back. The whatever error you are finding, that error is propagated back to the model to adjust the weight. We'll see that how it's doing. Okay. So now I'm just coming to the example directly. So the content type, whatever is mentioned here is whatever I have already explained the things. Wait. Yeah. So I'm just directly coming to the example here. So I'm taking the 5 words. So this is a skipgram model. Sorry, skipgram model is it is continuous bag of words model. It's a continuous bag of word model. Context is given. Left words, right words, center word. You are asking. You are not telling that what is a center word to the machine. You are asking algorithm to find the center word. System will give the first option. System will give that this is easy to sit. I'm having the word sat. So I'm saying no. No means, as I said, that I should not say no. I should say give in terms of numbers. How much no? It means that you have to quantify that no. How much error? So I'm finding the error is sat minus sit is the error. This error value, and with the help of the error value, I am tuning the weight values. Usually in the neural network, we used to assign the weight randomly. We used to assign the weight. Later on, once the iteration started, for each epoch, we used to update the weights. Same thing we are going to do here. See here, initially I just to go with the random weights. But what I want is I want to achieve the weight, the perfect efficient weight vectors. So that I don't know initially. With the random weights, I am just getting each word I am just treating. Initially, I am just treating that as a one-not representation. I am multiplying with the vector. I am finding the hidden layers. So I hope you remember that I said about something about R100 and then R300. So which says about the dimension of the vectors, word vectors. So that is decided by this hidden layer. The size of the hidden layer, the dimension of the hidden layer says about the size of your vector. Suppose if you want a 100-dimensional vector for each word, you fix 100 neurons here. So the random W here, the input you are passing to the random W, and you are getting some output. So you are not satisfied with the output. You are, as I said, that you are finding the error between sit and the sat. You are finding the error. That error, what you will do is that error, based on that error, you will update this W, because initially you go with the random W. After some iterations, you want efficient, you want a perfect W where you want the efficient word vectors. So you are tuning this W based on the error it's giving. This is not a new algorithm. Again, by repeating, this is a simple, basic neural network. single layer neural network. Input layer, hidden layer, output layer. Whatever output you are getting, you used to back propagate the error. The error, whatever you are having, you are back propagation means you are updating the weights based on the error. Based on the error, we are updating the weight. Finally, once you identify the words sad, then I stop the iteration. So that time, whatever the values in this W table, W matrix, that is called as a word embedding matrix. You see, look at the size of the matrix. It is a V cross N vocabulary. All the words in the corpus vocabulary into N, the size of the each word, size of the vector. So each word, suppose you are representing each word into 100 dimension. Each word 100 dimension. Each word 100 dimension. So finally, the matrix size will be, suppose you have a 5000 words means 5000 cross 100. So this is how we are calculating the word embedding. So far, again repeating, I'll start with the word embedding, the important concept. Simple word embedding. This is a very basic model for all the recent concept. Even the recent, there are a lot of algorithms are there. This is the basic model for this is the basic model for this the recent advanced embedding concept like a bird, distilled bird, all bird kind of embeddings. Daily new models are coming. Actually, the popular one is the bird. Now the current popular one. But the basics for the bird is bird to bird. So this slide shows the other power of word to vec model. So I am giving the word, I'm finding the cosine distance. I have given the word Sweden. I have given the word Sweden. I try to calculate the cosine distance between the other words. So the cosine distance is roughly says about the geographical distance also. The country Sweden is closer with Norway, so see that cosine distance is closer. Geographically, I'm saying that. Geographically, the Sweden is a little away from the Netherlands, so see that it shows in the cosine distance. So that way, I can say that the word embedding model, whatever we are trying, is captures the meaningful, efficient representation. This I already discussed about the relationship and linguistic regularities. So this is the other linguistic regularity, the direction. Says about the country and capital. See the country, where the country is, where the capital is. So France is there, Paris is there, Greece is there, countryside Greece is there, Italy is there, Greece, and then this side if you see that. So all the things are matched. If you see that, matched means the direction. You see this direction. So Italy is in the wrong direction, and then Spain if you see that. So this direction says about, earlier we have seen that this direction is a linguistic regularity for gender. Now this direction says about the capital. So like that, lot of inference can happen. So this also I explained. King minus man, it's a very famous equation. King minus man plus women equal to queen. So this is the diagram where I explained in the last presentation. I hope you are aware that. So we are discussing about the dense embedding. So this part we are discussing. So now you are giving the documents to me, and I have come up with the dense embedding. Dense embedding means meaningful representation, meaningful low dimensional representation. This is the initial point to the deep learning. So once you are identified the dense representation, you can pass that information to the deep learning model. So these are the shared tasks. I think this I have already explained. I have given this explained in the last slide. So this also I already explained those things. Just to have a look onto it. So what I need to say as a takeaway is, so the word embedding, now this is a basic model. Whatever I thought is a basic model, this is a stepping stone to the word embedding. Whatever you are having. So you cannot directly understand the word model. If you understand the word to vec model, what I explained, SIBO on the skip brand, directly you can go for the word model. Now recent models are there. So I have a quick question to you people. Then I'll stop, and then I like to hear some questions from you people. I have a questions. Which model is efficient from your perspective? Whether it's a skip brand or a SIBO model. So I'll stop here. So I want to ask you that which model is efficient, whether it's a skip gram or SIBO. This is, you know that this model is example for SIBO. Which model is efficient in terms of performance? So now, after this question, I am stopping. If you have any question, you can ask or you can post in the chat box. I'm happy to answer. So please note my email address also. I'll just put it in the chat box. If you have any clarification or any data set if you want, you can contact me. So which is a complex model? People are telling that SIBO, SIBO, SIBO. Why we are going for machine learning? So the simple reason why we are going for machine learning is certain things we cannot solve with the help of human alone. We need, as I said, that the iteration. So if you are connecting the CPU or GPU system, the system will go for several iteration, 1 lakh iteration, 1 lakh mathematical calculation it will do, and then it will find out the correct solution. The solution means in terms of weight vectors. Human, it's very difficult for us to do. So the reason for why we are going for machine learning is the complex problems. Okay, whatever I have given the problem in that to identify the word love, this is the easiest one. You have seen that you understand that you within a 30 seconds you say that sir the word is love. Machine, if I give you also, machine will say in a 5 seconds or 10 seconds, machine will say that yeah, this word is love. So machine will not tune the parameters much. See that machine will not, because it contains lot of information in the context. But you just think the reverse one. I'm giving only the word to the machine. Machine, I'm giving only the word love. I'm asking the machine to fill all the words in that slide. I'm giving to you. I'm giving only the word love to you. I'm asking to fill all other words, all the remaining words in the slide. I'm not showing the slide to you. I'm keeping it myself. I'm asking you to fill all the remaining words. Is it possible for human to fill? We can fill. It will take 1 or 2 days. With the several iteration, we may need to go. With the several iteration, we can fill that slide. Same way, machine also will do with the several iteration. If it's doing with the several iteration, then obviously the parameters are tuned. Parameters are moved away from the random parameters. Initially, we have started with the random parameters. So in the SIBO model, it will search the points near to the random parameters. But here, as you are doing so many iterations, you are getting the error and you are updating the weights. You are moving away from the random parameters. So whatever the vectors you are getting in the skipgram model is far better than the SIBO model. So that's a conclusion. Now I'm just happy to listen or answer some of the questions. So I shared my email ID with you. So I think this is related to the application. No, definitely it's not related to application. Word embedding is a common term. That's what in the diagram, I hope you remember that word embedding is we are putting in a separate place. Currently, I'm working in sentiment analysis. I found emotion reduction is one of the important part. Okay, can I use this one? Yeah, stock market we can do it. So how that how the sentiment in the news, how the sentiment in the news. I'm saying that emotion in the news. News means news about Satyam Mahendra or news about Robert Bosch. So that kind of news, and from there you match with the sentiment, and from the sentiment you can match with your the stock market values. Definitely you can do that. Any other questions? I'll share the slides with the Murugan sir. Murugan sir? Okay. Organizers are there? Organizers? Can you hear me? Fine, no problem. So anyway, I'll share the slides with them. So the 2 slides I'll share with them. I shared my email address also in a chat box. So if you have any clarification, you can ask. If you want any data set, if you want any guidance towards this area, you can contact me. You can mail me. Fine. So thank you. Now I'm stopping. I thank Murugan sir, and then I thank the other organizers and IRTT and then Atal AICT for inviting me for this wonderful lecture. And finally, thanks to participants and thanks to my beloved Professor Parimala Kanagadevan sir also. So thank you, sir. Thank you all. So I'm just leaving. I have a meeting at 1 o'clock. Just leaving now. So thank you all. So I'll be connected through if you want. If you have any clarifications, definitely you can contact me through email. So definitely I'm happy to clear it out. So thank you all.
Hello, Murugan sir. Hello, Murugan sir.
Sir, he is not available, sir.
Yeah, but
Yeah, that's why
nobody.
I put
Yeah,
message.
because nobody is taking cognizance of whether the lecture is going on or having technical problem or whether it is ended or what.
Hello, participants. Where are they? Participants.
Yes, sir, we're
Yeah,
waiting
good
for you,
afternoon.
sir.
Yeah. We can finish the conclusion session.
Yeah,
By 2:30, you can join for the next session.
yeah, okay, sir.
Okay. Thank you.
Sir, attendance form, please.
Yeah. I will put that. You wait. I will put the link.